So let me just take a quick aside and make sure that there's sort of this nice story that goes along with the simple models of running that I can't help but tell you guys. So quick aside, let's talk about the value of these simple models. Let's say virtue number one, right? The one we've been capitalizing on is that the simple models are analytically, computationally, pictorially simple to get our head around, right? So analytically sometimes, even graphically tractable. And that's a big deal for us. And that's really the reason that I've been talking about them, in the class so much. I think really that infers deeper understanding of the fundamentals. Okay, but some people, let's say virtue number two, some people are actually able to use those simple models to make a more general statement. Okay, so sometimes you can actually, they can yield general results or conclusions. Okay, so insights. So here's an example that I didn't quite get to before, but it's worth mentioning now. So remember the simple model of walking, where we had a pin joint in the back foot, let's say. We had the foot about to come into contact, and our model for the energetics of walking was dominated by the notion that the center of mass, your momentum right before contact had to look like this. It had to be a right angle here. Your after contact, it had a right angle here, and there was this story about losing energy like that, right? So one of the things that people have extracted from this sort of very simple model is a nice energetic story about walking. So they said, for instance, this is Andy Ruina's story, one of his many stories. He said, what if you could put sort of push off with your toe right before impact? Okay, and in the simple models, let's call it an impulsive push off, so it happens instantaneously. And that's just equivalent to what's the role of pushing off with your back foot right before you contact. It turns out the timing of that can have big implications on the energetics of walking. In particular, if you manage to toe off just before this foot comes in contact with the ground, then an impulse here could change instantaneously. Does the green show up okay? Yeah. Can change instantaneously. This could be from an impulse. Your total momentum, so that at the moment of impact you lose much less, right? Do you have any colors left? Not really, but right. If I can use an impulse, if I can use my push off it right before I'm coming down to the ground, I've got all this energy that's about to be lost into the ground. If I can push off right before, then I can reduce the ground speed of my foot, suffer much less of an inelastic collision, lose much less energy, and it's a very simple sort of picture that you can see right here, and it can sort of dramatically reduce your losses due to collision. Right? So Andy has this great quip. This is Andy Ruina at Cornell, who's one of the prominent names in passive dynamic walking and walking robots. He had a nice paper with his colleagues saying that you can be 4 times more efficient to toe off before heel strike. As opposed to if you wait till your heel strikes and then push off, that's a lot worse. And by dimensionless arguments, he's actually able to give some sort of quantification to it that in dimensionless terms, you can actually have a 4 times factor of efficiency. Okay, so that's just a simple, nice story that tells you something about, I mean, that's going to generalize to more complicated robots, right? That I can reduce the ground speed of my foot that's about to come to collision with a toe off. And that can be a big role that it has to play, right? And that's a story that comes out of the simple models but generalizes much beyond that. And I would argue that it would have been, if we had been looking at Asimov models the whole time, or Atlas models, or some complicated models, we would never have had such a clear story about that. Okay? But there's another virtue, the one that comes up today, that comes into play, which is that some of these simple models have actually, sort of using that sort of idea, have actually started to give back and been used by biology to start making predictions and summarizing data in biology. So there's a movement that Bob Full at Berkeley likes to, has been one of the leaders of, that they call comparative biology. Where they're using simple models to find principles that hold across a wide variety of animals. Okay, so the picture I showed, which is one of the topics we're going to focus on today, of running as sort of this motion like this, it turns out a nice model for that is to have is if you had a spring in your leg that compresses with a constant stiffness. It's called the spring-loaded inverted pendulum model. Slip model. Okay. Constant stiffness spring. In the leg. And looking at it turns out that simple model not only is going to be interesting for our robots, but it turns out that simple model has been very predictive in biology. That if you look at the center of mass and center of pressure dynamics of animals when they run, and again, that's the center of pressure, not the foot. So if you've got some animal, I don't know, a boxy horse, right? So just drew the horse's leg backwards, but you know what I mean? Right? So I've got a center of mass here. I've got a center of pressure here. But what would make it better? I mean, so it turns out if you model the horse as a spring mass runner, it's like, I'm an engineer, not an artist. Then the gross center of mass dynamics of the I almost said the robot, of the horse actually match surprisingly well with the dynamics of a spring-loaded inverted pendulum, okay, with a constant stiffness over the course of a stance phase. But what's really surprising is that not only does that model work for a horse, but it also works for a cockroach, right, which is sort of 5 orders of magnitude smaller in terms of just mass, right? And in fact, they could even predict sort of the stiffness, the relative stiffness compared to the mass, and even that matches sort of surprisingly well. I grabbed a figure from their paper here. Look at this. This is the relative individual leg stiffness. If I model these guys as a constant stiffness spring, and they normalize for mass, right? Then the relative stiffness sort of looks like a surprisingly good model, and happens to be a relatively constant number across a surprisingly large range of animal models. Okay, so it turns out to be predictive in that sense. And notice that what's really interesting about this is that the variety of gaits in here is extreme, right? So a cockroach has 6 legs. The kangaroo's hopping mostly on 2, although they use their tail, right? The human's got 2 legs. That's their robot, Rex, right? But rabbits, quails, horses are in here somewhere. This one maybe. I mean, different numbers of legs, different gaits, but they're all sort of running with this sort of characteristic spring. So maybe that means they found something primal about biology by using these simple models. Okay, I think it's hard to generalize to anything in biology. If I've learned one thing talking to the biologists is that biology is messy and complicated, but that seems like maybe a defining principle. And there's some question of whether that's a principle that was talking about the central part of the motor control system, or if it's because they've got springy tendons in your legs. There's been a lot of work relating the stiffness from these models to the tendon stiffnesses in your legs. So it might be a physical reason, it might be a cognitive reason, although cockroaches don't have that much cognitive ability. But there's lots of interesting questions there, but it seems at least predictive across a large range of animals. And sort of the last virtue is one that I want to say carefully, and so I'll just put it in the corner because I want to say it carefully, right? Because, but some people use this as a template for complex robots. And I'd say the jury's still out whether that's the right thing to do, but one argument is if horses run with a center of mass model that looks like this, and I built a robot that has 62 motors in it, maybe what I should do is I should try to take my big complicated system and make it act using sort of control feedback design to make it act like a spring-loaded inverted pendulum. And that may be the right thing to do, given that mechanical machine that's not a biological thing, it might not be the right thing to do. But that's an active area of research, is sort of the idea of embedding simple models as the controllers for a more complex model. Okay. So let's dive in and start looking at the dynamics of the slip model using our Poincare analysis and everything. Okay, it's a nice example. It follows what we did last time, but it's a little bit richer. So I think it's a great example for today.